Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. This is subsection 7.1.2 on time complexity notation. So, in the last subsection, we saw an example of comparing how many lines it takes for in the Euclidean algorithm for n is the larger one, m is the smaller one, to compute the greatest common divisor between them. And we found an upper bound. We always know this is smaller or less than or equal to this guy. Okay, there's some notations that we can use, actually. We can say perhaps that the time complexity is asymptotically less than this guy right here, or is equal to the big O of this. These are two different things we could write and say. What do they mean? Okay, so let's think about that. The ratio between this and this is going to be, so yeah, what do these notations mean? They're not just simply inequalities. What it means is asymptotically as these guys, as n gets large, then it will be inequality, maybe to a constant multiple of this function. So that's the same thing as saying that the ratio is bounded. The ratio of what actually happens to this constant function is bounded. So that's kind of what it means when we write this. Okay, when we write both of these things are equivalent, they mean the same thing, and they basically mean that. So that's really all the notation means in a technical sense. It just means that the ratio between what's happening and the function that we chose is actually bounded by something. So if we chose something really big, of course, then this ratio is going to be fairly small and eventually maybe even to zero or something like that. So definitely bounded above. If we picked something that was too small, then maybe this would grow without bound and not be bounded. So this really does say something, okay, that the ratio is bounded here, and that's kind of what the notation means by some number, finite number k. All right, another way of saying that is this is always less than k times that function for some constant k. It's bounded above by, okay, a multiple of this guy. So in general, this limit might not exist. However, all we need, like the limit of this ratio as n goes off to infinity. Sometimes that, because maybe you have too much bouncing around. But nonetheless, all we just need is for it to be bounded by a constant. So this is nice when we're working with something that's not continuous, very discrete, very irregular in behavior. Yet if we can just say something about that the ratio to something nice is bounded, that says a lot, even if we don't really have a limit existing. Another one way of saying this is that we look at the collection of all these ratios, and we can say that it has a least upper bound, we could say, okay? So there's an upper bound, and of all the upper bounds, take all the upper bounds, there's actually a least upper bound. Now, that least upper bound would be a nice constant to use. So if we can make that constant as small as possible, of course, that would be very nice here in our analysis. Another way of saying least upper bound, if there is a smallest one, is supremum. In the real numbers, actually one of the axioms that is used is every set has a least upper bound. So that's one thing that we can, every bounded set has a supremum. That is, I mean, I guess, it needs to be bounded for sure in that condition, unless we're extending it to include infinity. Okay, essentially, okay, so, okay, back to our example. As n gets large, okay, means eventually for large enough n, the behavior will stabilize and the ratio will be less than k. Okay. So you see this eventually right here. let's just take a look at kind of what's happening here as we go along. It's just an example of things that might be happening. Maybe eventually over time, at first, maybe K is not a good upper bound, but maybe eventually it becomes an upper bound forever onward after a certain point. So as we keep moving through, maybe these points will eventually get smaller and smaller. And so at some point we can use even smaller upper bound and maybe even smaller upper bound as we go. Now, of course, this wouldn't be good if we had things happening up here beyond. In fact, there would be no supremum constant if this just kept going off forever. So like this, then we wouldn't we wouldn't be able to use that notation. We wouldn't be able to say that it's asymptotically less than it something. We wouldn't be able to compare f of nm to something continuous, something like this if it's without bound, even though if it's jumping around. So the statement that we want kind of ensures that we have some control of the behavior. Eventually, it's going to be less than, this ratio is going to be less than K. We want that ratio to eventually be less than. There's different ways of saying this. This is one, we have these two ways which we discussed. This means, this reads as the big O of log base square root of 2 of n. This is f of nm is asymptotically less than log base square root of 2n. So that means there's some constant k. But also, we have this idea as well, which adds a little bit to it. The lim sup. Well, sup means supremum, and this means the limit of the supremums. The supremums actually, okay, so that's an interesting idea. Let's look at some pictures related to that right here. So what if we're at this point? The supremum, which means the least upper bound, would be like at this place right here, right where this point is. And maybe it's bigger than everything that comes after. But if we move to the next one, actually maybe this point is bigger than everything comes after. So that's the new supremum. When we keep on going, when we get to this point, we have even a new supremum, because everything below this one is less than it, and so forth. In fact, the supremums as we go, and if we can hit another supremum and so forth, they're actually a decreasing sequence. And if you've seen something in calculus, there's something called a monotone convergence theorem, which would guarantee it has a limit. So you can actually take the limit of the supremums as you go along, then they'll be getting smaller as you go. If that limit exists, well, if that limit exists, then for sure you have, then for sure along the way, you actually have these guys, which are supremums, past a certain point, and that's all we needed, really. That's all we wanted. We just wanted, after a certain point, the ratio to be bounded between the two. That's really all we wanted. That was enough to ensure that we have a nice way of describing the behavior between the two, between the function and the radical behavior of f of nm. We didn't need it to go off to infinity. We just needed in general that ratio to be bounded. But so this statement's a little strong. However, sometimes it's used, so it's mentioned here. Okay. Okay, so these notations have their own properties and things associated with the big O notation or the asymptotically less than notation. Okay. And that'll be covered in the next little subsection. But for now, let's look at, let's see this example. Okay. Oh, this example of lim sup. All right. Which is essentially just a limit, because the supremums in this case are lim sup for a continuous function is just equal to a limit. So it really only has meaning when we have things bouncing around. I guess that's what we were, this example was emphasizing. Thanks for watching.